In this session, we're going to talk about heaps. And we're going to talk about many different types of heaps. I expect that you know from your undergraduate courses what a heap is, but I'm going to review some of the main ideas there. So the most classical type of heap is a binary heap. And a binary heap is an almost full binary tree. So a tree like this. Even have one more here, maybe. And we store some number or some element at every node of this tree. And we assume that the elements can be compared with each other. So if they're numbers, of course, we can compare them. And it has to satisfy the heap rule, which means that the number written at every node should be larger than or equal to the numbers written at its children. So if I have a 10 here, I can have maybe an 8 here, a 7 here, I don't know, a 7 here, 1 here, 6 here, a 1 here, and 2. Okay, so this is called the max heap because the maximum element is on top. You can have a min heap where the rule is to have the smallest element on top, and then each element would be smaller than its children. But in this lecture, I'm going to mostly work with max heaps. Okay. And generally, in the different types of heaps that we have, the main difference is in the structure of these trees. So in a classical binary heap, this tree is an almost complete binary tree. And you've probably seen that you can actually store this tree into an array of size n if you have n elements. And the way that we would do that is that we just give an index to every node. So let's say this is my node 1, this is 2, this is 3, this is node number 4, this is node number 5, node number 6, node number 7, and node number 8. And generally, if I have a node that is stored at index k, then its two children would be at index 2k and 2k plus 1. Right? So for example, here I have a node that is saved at index 2 of an array, and its children would be at indexes 4 and 5. This is pretty handy because if I have n elements, I can just save them in an array of length n. And then I can just think of that array as a binary tree that looks like this. But now, what are the operations that we usually want to perform on a heap? Well, there are two main operations. One operation is push, which takes some element x and adds it to the heap. And of course, we have to add it in a way that satisfies all the heap properties. And the other operation that we have is called Popmax, which removes the maximum element from the heap. Now, of course, if you have a min heap instead of a max heap, you can have popmin. These are the two main operations, but we have some other operations as well. So we can have, for example, an operation called increase key, which gives you a pointer to somewhere in your heap. For example, it says this element, and it says increase it from 1, for example, to 5. Okay, and then you have to make sure that the heap properties are still satisfied. So we can have push, we can have popmax, we can have increase key. We can just have max, which asks you what is the maximum element without actually popping it and removing it. But again, we're going to mostly focus on push and popmax because everything else is very similar. So for those of you who remember your undergraduate courses, how much time does it take to do push in a binary heap like this? It's going to take order log n time. And the way that we do push is that we just add the new elements at the new index. So for example, here I'm adding the 9th element. So I just add it at index 9. And let's say that's the x that I was trying to push. the actual value, let's say it was also 9 for this example. So now the problem that I have is that the heap property is not satisfied here because this element is larger than its parent. Now, how do we make sure that the heap property is satisfied? We just swap them. So let's just take this 9 and move it up and move the 7 down. So the 7 comes here, the 9 goes here. Now we have the same problem here. So this 9 is larger than its parent. We just swap it again. So the 9 goes up, the 8 goes down. And by the way, usually this operation of swapping some element and taking it up the tree is called bubbling up. So I bubbled 9 up, and now I'm at a point where 9 is finally smaller than its parent. So this is a valid heap. I don't have to do anything else. Now, how much time does this take? Well, I add a new element and I have to move it all the way up my tree. So the runtime is going to be the height of the tree. But what is the height of the tree? The height of the tree is log n, because this is an almost complete binary tree. Okay. So for push, we can do that in log n. Now, what happens if I want to, let's say this one, do increase key? If I have an element here, for example, this 2, and I want to increase it to, let's say, 8. It's just like the push. You change it, and then you have to bubble it up the tree. So again, this one is also going to take log n time. What happens if I want a maximum element? My maximum element is always in my root. So that's order 1. That's super fast. Now, what happens if I want to pop the maximum element? What happens if I want to remove this maximum element here? Well, my tree has to keep its shape, right? So if I remove some element from a tree with 9 elements, it has to have this shape, right? So I can't change the shape of my tree. So the element that has to be removed is this one. So what I can do is that I can first swap my top element, my root element, with this one. So I put 10 down here, and I put 7 up here, and then I can remove this element. So I remove this. Now, the problem that I have is that this 7 up here, it might be actually smaller than some of its children, and it is actually smaller than this child. So what I have to do is that I have to take this 7 and I have to move it down the tree. This is called bubbling down. And every time, so if I have 7 and I have 2 children, I want the maximum of these children to come and take the place of 7, and I want 7 to go down. So this 9 and 7 will be swapped. 9 goes up, 7 goes here. Now, again, I have the same problem here. So the 8 and the 7 will be swapped. 7 comes here, 8 goes here. Okay. And then this is, again, a binary heap. So the runtime analysis is very similar. You take the last element, you swap it with the root, that is constant time. And after you do that, you have to bubble down the root. The root can go down by at most log n steps, because the height of the tree is log n. So the overall runtime of Popmax is also order log n. Okay, so these are the things that I expected you to know even before this course. So the push takes order log n time, the pop takes order log n, increase key takes order log n. Actually, you can even have decrease key, it would be similar, and max is constant time. Now, what we're interested in is, of course, amortized analysis, because this is the module that we're considering right now. So the question that we have is, what happens if we have a sequence of operations instead of just one operation? Can we make a sequence of operations any faster? And honestly, the answer is no. So if you want to make a whole sequence of operations much faster, you can't do it. Let's say that I have n push operations. So I take n different elements and I just push them one by one into my heap. And then let's say that I do Popmax n times. So I'm taking one specific sequence, the sequence that has n pushes followed by n pops. this will give me what? It will give me a sorted array. And we know that we cannot have a sorting algorithm based on comparison that works in runtime faster than n log n, right? So no matter what I do with my heap, it's impossible to have a situation where all of my amortized runtimes are less than log n. Because if I can do that, then I can do sort in less than n log n, and I know that I can't do that. Okay. So what we're going to focus on is to try to maybe make the push faster, and then maybe try to make both push and increase key faster. But at any rate, we're going to let at least one of these operations take log n amortized time, because we can't do better than that unless we do something that is not based on comparisons. And heaps are all based on comparisons. Okay. So before going to a different type of heap, what happens if I give you an array that is just in some arbitrary order, and I ask you to make a heap out of it? Okay, so let's say I have, let me erase this and just draw something else. So we said that whenever we have an array of n elements, we can look at it as if it's a tree, right? So if I have a general array that is not necessarily sorted, what that looks like is a tree. And it might be a lot of nodes here. But the elements are not in any particular order. Okay, so I have some random numbers written all over. Now, what happens if I want to turn this into a heap? What can I do? Well, I can create an empty heap, and I can push the items one by one, right? And I know that each push takes log n time. So if I just push all the items one by one, in total time n log n, or n log n, I can have a heap. But can I do faster than O n log n? So what I'm doing here is that I'm, again, doing something similar to amortized analysis, but instead of saying that I take any sequence, I'm just saying, suppose that I have a sequence of n pushes. Can I do that faster? So if I only have the push operation and I'm doing it n times, can I do it faster than n log n? And actually, the answer is yes. What I can do is that I can just create that array, which has no specific order. So I now have this tree, and nothing has any order in it. And now, so I can do two different things. I can, for example, start from the top and then bubble everything up. So I can first bubble up the root, then bubble up these nodes, then bubble up these ones, and so on. And at the end, I will have a heap, right? Or I can do the opposite. I can start from the bottom and I can bubble down. So I can start from the bottom and first bubble these nodes down, then bubble the nodes at the next level down, and so on, until I get to the root. Okay. And when I get to the roots, I've bubbled everything down, and then I have a binary heap. So let's analyze the runtime, especially of this second type. First of all, why is this correct? Why can I start from the bottom and just do bubble down and then go up and continue this? Well, because whenever I get to a node here, I can use an inductive argument, and I can say that this subtree and this subtree are both valid heaps. So if I look at the subtree that starts at this node, that's a valid heap except for this one node here. So it's very similar to the case where we were doing Popmax. So I can bubble this one down, and then all of this subtree would be a valid heap. So the algorithm is correct. I can start from the bottom to the top and just bubble down everything. But what is the runtime? Well, let's just count. So let's say I have different levels. So let's call this one level 0, Let's call this one level 1, level 2, and so on. And let's say that the last level is level k. Okay. So how many elements do I have at every level? So what is the number of elements at level 0? It's just 1, right? Because I just have the roots. What is the number of elements at level 1? It's 2. What is the number of elements at level 4? It's 4. And so on. What is the number of elements at level k minus 1? It's 2 to the power of k minus 1. And what is the number of elements at level k? Well, my heap might not be full. So I cannot be sure that I have 2 to the power of k elements there. But what I know for sure is that I have at most 2 to the power of k elements. Okay. Now, how much time am I spending at each one of these elements when I'm doing bubble down? So if I'm starting at level k and I'm doing bubble down, that's going to take at most constant time for each element because I'm just going to pass over the elements and not do anything. So this is constant time, or let's say it's 0, right? If I just count how many times this element can go down, it can't go down, so it's 0. How many times can an element at index k minus 1 go down? Well, 1 time, right? And we can just continue this, and then we go all the way up here. And at level 0, it can go down k times. At level 1, it can go down k minus 1 times. At level 2, it can go down k minus 2 times. So what is our total runtime? Our total runtime is going to be 2 to the power of k times 0 plus 2 to the power of k minus 1. Yes, times 1 plus 2 to the power of k minus 2 times 2, and so on. And we can just sum this up. And that would be order n. I don't like to do algebra, but just believe me, because we have a lot of nodes that are taking very little time, and we have very few nodes that are taking a lot of time. So overall, it's going to be better than n log n. Okay, so this is a technique that you have to keep in mind because we will use it in our other types of heaps. And the technique is that whenever you're doing push, you can just be lazy, and instead of actually making sure that your heap makes sense, you can just add that element anywhere. And then after a while, after you've done a lot of pushes, you can clean up everything. And that's faster than doing the pushes one by one. Okay. So I'm going to erase this one. Okay. So finally, we can get to the graduate part of the course. And in this part, we're going to look at a different type of heap. And this is called a binomial heap. Now, the idea in a binomial heap is that instead of just keeping track of one tree that is our heap, we can maybe have many different trees. But we want to make sure that our trees have a very specific kind of form and shape. So our trees are what's called binomial trees. And this is how they look like. So a binomial tree of degree 0 is just one node. Okay. And when I say a tree of some degree, I'm basically talking about the degree of the root. So the number of children of the root. So if you have a tree and its root has no children, of course, it's just one node. So a binomial tree of degree 0 is just this. A binomial tree of degree 1 is obtained by taking two binomial trees of degree 0 and basically merging them, making one of the roots a child of the other root. So a binomial tree of degree 1 looks like this. Now, if I want a binomial tree of degree 2, I have to take two binomial trees of degree 1 and I have to merge them. So it will look like this. I will have two binomial trees of degree 1, and I'm going to make one of them, one of the roots, a child of the other roots. Okay. This is a binomial tree of degree 2. Now, of course, if I want to have a binomial tree of degree 3, I take 2 binomial trees of degree 2 and do the same thing. So this is a binomial tree of degree 2. And I take another one of the same. And then I make this one a child of that. So this is a binomial tree of degree 3, and so on. Okay, so whenever I want to have a binomial tree of degree k, I take 2 binomial trees of degree k minus 1, and I make the root of one of them to be the child of the root of the other one. Okay. So let me ask you some basic questions about these binomial trees. How many nodes do we have in a binomial tree of degree k? Yes, 2 to the power of k. And it's very easy to see that. Again, you can do that inductively. A binomial tree of degree 0 has 1 node, and a binomial tree of degree k is basically 2 binomial trees of degree k minus 1. So you have 2 to the power of k. And what can I say about the height of these trees? What is the height of a binomial tree of degree k? Yes, well, it depends on how you define the height. Like, do you count this as 1 or 0? But it's order k, right? Because as we're going to the to larger k here, our height is increasing by 1 every time. Okay. So now I can define what a binomial heap is. A binomial heap is just a sequence of binomial trees, so that all of these trees are satisfying the heap property. Okay, so binomial heap, what it is that it's a sequence of binomial trees. Oh, and one important point here is that all of these trees should have different degrees. So I cannot have 2 binomial trees of the same degree in my heap. So my binomial heap is just a sequence of binomial trees of distinct degree. Okay. And additionally, I expect that each tree satisfies the heap property. Which means that in each of these trees, when I look at any of the nodes, the number saved at that node should be larger than or equal than the numbers in all of its children. Okay. And so one important point here is that, of course, our degrees are no longer bounded by 2. So we're not really working with a binary tree anymore. I can have nodes of any degree, but if I have a node of degree 3, then the value stored here has to be larger than or equal to the value stored at all of its children. Okay. Now, another thing that I have to say here is that I said a binomial heap is a bunch of binomial trees. And I said that I don't want to have 2 binomial trees that have the same degree. But this doesn't mean that I have to have binomial trees of every degree. So it might be that I only have binomial trees of degree 0, then I don't have degree 1, I don't have degree 2, but then I have another one that is of degree 3. Okay, so the rule is that no 2 of my trees should have the same degree. It's not that I have to have all of the degrees. Now, how would I enforce a rule like this? So what happens if at some point I have 2 different trees that have the same degree? Well, if I have 2 trees of degree k, I can just merge them together and get a tree of degree k plus 1, right? So here's an example. Let's say at some point during my algorithm, and I'm not going to get into the details yet, but let's say at some point I have 2 binomial trees of degree 1, and let's say that this is, for example, 2, this is 5, and I have another binomial tree of degree 1, And let's say this is 3 and this is 4. Okay. I can easily merge these two to get a binomial tree of a higher degree. I have to make one of the roots the child of another root, but the choice is obvious because, well, I have to satisfy the heap property. So I have to take the smaller root and make it a child of the larger root. So if I have a situation like this, I will just turn it to something like this. I have 5 and I had 2, and now 4 becomes a child of 5 and 3 was a child of 4. Okay. So this is how I enforce the fact that I'm not going to have more than one binomial tree of any given degree. Okay, but now let's talk about how we can do these operations. So how would you do push, for example? If I want to do push, I just add the new element and I add it as a new tree for itself. So let's say that, okay, let's say I don't have this one. And let's say this is my binomial heap at the moment. Okay. And let's say I have some numbers in there as well. So maybe this is 5, this is 6, this is, I don't know, 10. And I have some other numbers in all of these nodes as well. I'm too lazy to add numbers. So let's say I want to add some new elements. So for example, let's say I have push 7. Okay, so I want to push a 7. What I do is that I just create a new binomial tree of degree 0, which is just one vertex. And I put the 7 in there. Okay, but now my problem is that I have two different trees that have the same degree. I have two trees of degree 0. So what I can do is that I can just merge them. I want to merge 6 and 7. Oops. Let's roll. So of course, 6 has to become a child of 7. So I make 6 a child of 7. But now my problem is that I have two binomial trees of degree 1. But again, I can continue the same thing. I can just compare the roots, and I can see that 5 is smaller than 7. So I just make this a child of this one. So 5 becomes a child of 7. And whatever was here, I don't know, let's say there was a 2 here, the 2 goes there. And I get rid of this one. So now this is how my heap looks like. Now my heap has 2 trees, one of degree 2, one of degree 3, but they have different degrees anyway. Okay, so this is how I do push. So now my question is, what is the runtime of a single push? If I do a push, how much time would it take? So let's say that I already have n elements in my binomial heap, and then I do a push. How many different merges do I have to do? Because the push is basically creating a new tree of degree 0 and then merging everything. So the question is, how many times do I have to merge? Well, I have this vertex of degree 0 or tree of degree 0. I have to potentially merge it with another one of degree 0. But then after that, I will get something of degree 1, and I might have to merge it with another tree of degree 1. That gives me degree 2. I might have to continue merging. But how long do I have to continue? Log n, yes. Why? Because we said that if we have a binomial tree of degree k, then it has 2 to the power of k elements in it. So no matter what the sequence of degrees of my binomial trees are, the largest degree is going to be at most log n. And because the largest degree is at most log n, I have to do at most log n merge operations. And every merge operation is taking constant time, because a merge operation is just that you take 2 roots, you look and see which one is larger, and then you make the smaller one a child of the larger one. So that's constant time. Yeah, so my push is going to take log n time. Now, what happens if I want to do, let's say, this operation? Let's say I want to do max. I want to find the maximum element. How much time would that take? That also takes log n time, right? Because what do I know about my max element? I don't know which one of my trees contains my maximum element, but I know that it's at the root of its own tree, wherever it is. So I can just go over all of my roots, and I can take the maximum of all the roots. And I have at most log n different roots. So this gives me O log n. But we can be a bit more clever, and we can always just keep a pointer to the maximum element. And if we do that, then we can always answer the max in constant time. Okay. How about this one? What if I increase some key? So let's say I have some values here. Let's say I have, for example, I don't know, 5, 2, 8, 7, 1, 1, 4. Okay. And let's say that I increase this 4. Okay. There are many cases. Well, one case is if I increase 4 to 5, nothing happens. I can just increase it, right? Because then it's still less than or equal to its parent. But in any case, even if I increase it really a lot, even if I increase it, let's say, okay, actually, let me take the worst case. Let's say I take this 1 and I increase it to 11. Okay, then I can just do bubble up. I can swap it with this 7. So the 11 is now here. Then I can swap it with this 8. So the 11 is here. And then I can swap it with this 10 so that the 11 comes here. So it's just a bubble up that we would do in a normal binary heap. The only difference is that we're doing it in a more complicated tree. But it doesn't matter for bubble up, because in bubble up, I'm always taking one node and I'm just comparing it with its parent. Okay? But as we said, the height of these trees is at most log n. Because we said that a binomial tree of degree k has 2 to the power of k elements and a height of k. So the height of these trees is at most log n. So when I'm doing bubble up, I'm going up at most log n steps. So this one was log n, this one was log n, this one was log n. All the operations are log n. Now let's talk about Popmax. How would you erase your maximum element? So let me turn this back into 1. And let's say this is the situation that I have. Let's say this is my heap. So this and that. My heap has 2 trees. And I want to remove the maximum element of this heap. So of course, first I have to find it. And it's this one. It's 10. But how do I get rid of 10? Well, I can just erase it, right? And if I just erase the 10 here, then all of its children become the roots of different trees in their own sake, right? So now I have trees of different degrees. But now I have to again satisfy this condition that I should have distinct degrees. I cannot have 2 trees of the same degree. So again, I start merging. So as long as I have 2 trees that have the same degree, I would merge them. Now, in this case, this is degree 0, this is degree 1, this one and this one have degree 2. So I have to merge this one and this one. Okay, and if I want to merge them, this one has 7 in the root, this one has 8 in the root. So the 8 goes up, the 8 becomes the root. So after the merging, I have to take this one and put it as a child of this one. So it would become something like this. I will have the 7, the roots there here, and then I will have 6, and then I will have 5, and then I will have 2. And I no longer have this one. Okay. And now I had to actually erase this and write it again. But in practice, what we do is that we're just changing one pointer. We're just saying that the parent of this 7 is this 8. So the merging, every merge is taking constant time. Okay, so now this is how my binomial heap looks like. Okay, how much time does this take, the Popmax? It's again log n, yes. Because when I take, suppose that my maximum element was the root of a tree of degree k. If I take a tree of degree k and I erase its root, what I get are a bunch of trees of smaller degrees. So I get a tree of degree 0, 1, 2 to k minus 1. Right? And then I have to merge all of these into the trees that I used to have. Okay? So I have at most log n new trees, and I'm merging them into my previous trees. And actually, you can do them in any order that you like, but I would usually do it from smaller to larger. So it's like adding 2 binary numbers. And the amount of time that you're going to spend doing that is going to be the length of the binary number. And actually, now that I talked about binary numbers, there is a very obvious link between binomial heaps and binary numbers. So you see, in a binomial heap, I can have trees, and each tree has a size that is a power of 2. Okay? So if I have, and I cannot have 2 different trees that have the same size. So if I have n elements in my tree, in my heap, overall, if I have n elements, then that basically means that I'm writing n as a sum of powers of 2. So for every n, actually, the shape of your binomial heap is fixed. It's like you write n in binary, and then you just look at the digits that are 1. And those are the degrees of the trees that you will have in your binomial heap. So for example, in this case, I have how many nodes? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so if I write 11 in binary, I have an 8, I don't have 4. So 11 is 8 plus 3. I have 2, I have 1, right? So hopefully I didn't make a mistake. I'm terrible at computing anything. So let's say this is 11 in binary. So now I can just look at the value of k. So the value of k is, this is 1, this is 2, this is 3, this is 4. So it tells me that I have to have 1 tree of degree 1, which I do. I have to have 1 tree of degree 2, which I have. Oh, what happened here? Oh. Okay, sorry, yeah, I had to start from 0. That was ridiculous, yeah. Okay, so I have to have 1 tree of degree 0, which I do. I have to have 1 tree of degree 1, which I do. I don't have a tree of degree 2, but I have a tree of degree 3. Okay, yeah, I have to start from 0 then. So now you can think of this operations that we have, especially the push and the pop, as the binary counter that we saw in the first session when we were just talking about amortized analysis for the very first time, right? So we had this counter, this binary counter, and we would just increment it. And we saw that if we do n increments, the overall runtime is not going to be order n log n, it's going to be just order n. And so with the exact same argument, I can say that if I do n pushes here, the total number of merges that I'm going to do is going to be order n, not order n log n. Okay? And this even holds if you have a sequence of pushes and pops. So what you can say is that you can say the amortized cost of every push is constant, but the amortized cost of every pop is log n. And for the other ones, well, for max, we saw that we can just have a pointer and we can have constant time anyway. And for increase key, we saw that we can do it in log n because we can just do bubble up. Okay, these are not actual times, these are amortized times. Okay, so if I do a sequence of operations, I can assign an amortized time that is constant to every push. Why can I do that? Because a push is basically the same as increasing this counter by 1. it's the same as the increment operation that we saw last time. And again, the amortized analysis is exactly the same as before. You put like $1 on every one here. And then when you turn the one into a zero, which is your merge operation here, you're using that dollar. Okay. So now we got binomial trees and binomial heaps, and they are a little bit better than binary heaps, right? So in binary heaps, all of these operations took log n. Again, max always took O1, that's fine. But all of the operations that we care about, these three used to take log n time. But now we have come to a point where the push takes O1 amortized. So yes. No, so suppose that, okay, I'll actually do that in more detail right now. Let's say that I have a sequence of pushes and pops. I can still say that each push takes O1 amortized cost and each pop takes O log n. So let's do that. Let's say I have a bunch of pushes and pops. And let's look at this binary representation and let's see what the pushes and pops mean in terms of the binary representation. So each push is just incrementing this number by 1. Whereas each pop is decrementing it by 1. Okay, so now let's say I want to do some sort of amortized analysis. What I can do, just like the counter example that we had, not counter example, the example of the counter that we had in our first session, we can do an accounting and we can say that whenever in this counter I turn a 0 into a 1, I put $1 on the 1 that can pay for my later computations. Okay. So now what would be the cost of a push? Well, if I do a push, I start from the right and I'm changing some ones into zeros. So I'm changing this 1, for example, into a 0. And I'm changing this 1 into a 0. But I already had $1 on this 1. And I'm just going to use that $1 for the cost of this change from 1 to 0. Okay. And then at the end here, finally, I will have a case where I'm changing a 0 to a 1. So I have to pay 1 unit of cost for the change. And then I have to pay another unit to put $1 here. So that takes 2 units of cost overall. So my overall cost for push is going to be 2, which is O of 1. Okay, and this one remains 1. Now, what happens when I want to pop the maximum element? Well, basically, I have to decrement this counter. So I have to turn it back. Now, this one is much easier to analyze. What I can say is that this has at most log n different digits in it. So the actual time that I'm going to spend is log n at most. But additionally, I'm going to create a bunch of zeros. And additionally, I'm going to create a bunch of ones. And I have to put some dollars on those ones. But I'm putting at most $1 on each one. Right, so overall, my total cost is log n plus log n, which is 2 log n, which is again order log n. So now I talked about the counter, but you can see what happens with the counter exactly with the merges as well. So every merge is the same as changing 1 digit of our counter. Okay, and then both of them take constant time anyway. So yeah, even if I have a sequence of pushes and pops, I can say that in an amortized manner, the push takes order 1 and each pop takes order log n. Okay, and then you can just continue this and imagine what happens if you also have increase key and max and so on. Nothing changes really there. So using this idea, our push is now faster, which means that if I have a use case, if I'm using these heaps in a real world algorithm, where I have a lot of pushes, but I have relatively fewer pops, let's say, then this is going to be faster than a binary heap. Because in a binary heap, I had to pay log n for every push, but now I'm paying only constant amount for every push. Okay. But can we do better than this? Can we, okay, so here's the thing. We have these operations, and I told you that if you just push n elements and then pop max n times, that's the same as sorting, right? So if I change my push time to 01, there's no way I can decrease my pop time anymore, right? But how about this one? Maybe we can have a way such that push takes 01 and max takes 01, and let's say increased key also takes less time. And again, we're talking about amortized time here. So I know that there is no way I can get rid of the log n in the pop, but can I have a data structure that gives me a faster increase key? And that's what we're going to see now. So before I erase this, any questions about binomial heaps? Okay. I'm going to erase these ones. So the next type of heap that we're going to see is called a Fibonacci heap. Okay. And as I said, our goal is to decrease the time for increase key. I want this one to become constant. So let me erase this. Now, how does a Fibonacci heap work? First of all, I can't tell you directly why it's a Fibonacci heap, but as we will go ahead and analyze it, at some point you will see Fibonacci numbers and you will find out why it's called that. So the idea in a Fibonacci heap is very similar to the idea that we had in a binomial heap. We're going to have many different trees. We're not going to have just one tree. And these trees are going to have different degrees as well. Okay, and remember, when I talk about the degree of a tree, I'm talking about the degree of its root, the number of children of its root. So I'm going to have a sequence of trees, and I'm going to enforce that they have different degrees. But I'm not going to enforce anything else about their shape for now. So these are not necessarily binomial trees. They can be trees of any shape, let's say. But the only condition that I still want to be satisfied is that I want them to have different degrees. Okay. So I have a bunch of trees. Again, they're not necessarily binomial trees. So I can have maybe something like this. Or maybe I can have something like this. Right? But I want them to have different degrees. So how do I make sure that they have different degrees? And of course, each one of these heaps each one of these trees has to satisfy the heap property. So the way that I make sure that they satisfy the condition of having different degrees is that whenever I see two trees that have the same degree, for example, this one has degree 2, this one also has degree 2, I just merge them. Okay, and the merging is again the same as before. So I just look at the roots, and if this one has a smaller root than this one, then this becomes a child of this. Otherwise, the exact opposite happens. Okay. So let me actually erase those numbers. Let's say this is how my heap looks like now. Okay, now I have to talk about what happens when I do any of these operations. And the lesson that I want to use is that I want to go back and think about what happened in binary heaps. In binary heaps, whenever I was doing push, I was paying log n. But I realized that if I just don't do anything, whenever it's a push, I just add it and don't really fix the heap property. And then after n pushes, I come back and make it a complete heap. That's going to be faster than doing the pushes one by one. So what we're going to do in a Fibonacci heap is that we're going to be lazy. When someone says push X, I'm going to be super lazy about it. And I'm going to just add X as a new tree here. So let's say I did push 5, I just add 5 as a new tree on its own. And I don't do anything else. I don't even do merges. So if someone tells me push 6 now, I would just push 6 as a new tree. And I wouldn't merge it with the 5, even though they have the same degree. So I'm temporarily allowing trees of different trees of the same degree to exist. And why am I doing this? I'm doing this because I want my push to be fast. I want to spend very little time in pushing. So pushing is now going to be all 1, right? And this is not even amortized. This is real runtime. Okay. Now, what happens if someone asks me for the maximum element? If someone asks me for the maximum element, I know that the maximum element is in one of the roots, but I don't know which one. So I have to go through all the roots. And now I don't have any condition on the sizes of these trees. So I don't know how many roots I can have. In the worst case, I might have n roots. So now maximum is really time consuming unless I figure out how to somehow find a bound on the size of my trees, which I will do later. But we can just use the trick of keeping track of the maximum. So just keep a pointer to your maximum element. And when you're pushing, if the element that you pushed is larger than your current maximum, just update the pointer and make sure that you always know where your maximum is. Okay? So this will not really increase the time for push because it was constant and I'm now updating one more pointer. It's still constant. But it really helps with the time of max. So max also now becomes constant. Because if I want my maximum element, I have a pointer to it. I just look at it and return it. Okay. But now these two operations. What happens with these two operations? Again, if you remember, I said that you cannot have a fast push and a fast pop. So I'm giving up on the pop. But I want to make increase key fast. So what happens in increase key? Let's say I have some values here. Let's say I have 10 here, 8 here, 2 here, and even more. Let's say I even have like a 1 here. And let's say I'm increasing this 1. Now, there are some cases where it's really not important and I don't have to change anything. For example, if I increase this 1 to 2, it's still less than or equal to its parent, so I don't have to do anything. So in these cases, I just increase it. But another case is that I increase it and it actually gets larger than its parent. So let's say I increased it, for example, to, I don't know, 11. Now, in all of the previous versions of heap that we saw, we would take this 11 and we would bubble it up, right? But the reason we could do that was because we had a really nice bound on the height of our trees. But at the moment, I don't have any bound on the height of my tree. So if I want to bubble this thing up, it might go on for a very long time and it might take linear time. I don't want that to happen. So instead of doing that, I'm going to say I'm very lazy. If I increased it and it was larger than its parent, then I just disconnect it from its parent and I add it up here as a new root, as a new tree. Okay? And I can have cases where this also has children. So let's say, for example, I have this 8. Let's say it has another child, which is 5. And let's say I increase 8. Okay, no, I don't want to do that with 8 because 8 has the root as its parent. Okay, let's say I have a 3 here. I have a 4 here. Okay, so let's say I increase this 3 to become, okay, no, I increase this 5 to become 9, for example. If I increase this 5 to become 9, then 5 is larger than its parent, which is 8. But instead of bubbling it up, I just disconnect this and I say this is now a new tree. This is one of my trees. So I just take this 5 and I upgrade it to a root. Again, very lazy. So how much does my increase key cost? Well, I'm just comparing it with its parent, right? And if I didn't have to change anything, I wouldn't change it. If it was larger than its parent, I just disconnect that edge. So this is also constant time. Okay. But now the problem is what happens with Popmax? It seems like we were really lazy in all of our other operations and we did all of the other operations really fast. But now the problem is what happens if I want to pop my maximum elements. Okay. The maximum element is 10 here, right? If I want to pop it, I can do something similar to a binomial heap, if I want to be lazy again. And I can just say that I just remove it, and I say that all of its children are now roots. Okay. But what is the problem? The problem is that we should also have a pointer to the maximum element. So now after I removed it, I have to go through all of these elements, all of the roots, and I have to find the maximum. And in the worst case, that's going to take linear time. That's going to take n time if everything is a root, right? So my worst case here is that after a bunch of these operations, all of my trees are just trees with one node. And then everything is going to take, every time I update the maximum, it's going to take order n, because every time I get rid of the current maximum, then I have to go and search in all of my roots to find the next maximum. So I want to avoid that. How can I avoid that? Well, let's go back and think about binomial trees. In binomial trees, the reason that we could do this operation of Popmax faster was because we always had a bound on the number of trees that we had. We could always say we have at most log n trees. So if I want to find the next maximum, I have to just go over log n different roots. So let's do something here to make sure that our trees are large. Because if I can somehow make sure that my trees are large, then I can make sure that I have very few trees. And if I have very few trees, then when I want to pop max, I can just erase the maximum element and say, hey, I have very few of these. I just take the maximum among all of the roots. Okay, so this is our goal. Our goal is to have a small number of trees, which means that we want to in turn have a large number of nodes in each tree. But okay, so let's use the same idea as in a binomial heap, where we said that we do not allow trees of the same degree. We do not allow different trees of the same degree. And I can enforce it when I do the pop max. So I can say that whenever I remove this maximum element, not only do I remove it and upgrade all of its children to be new roots, and not only I find the maximum of all these roots, but I also want to do a cleanup, and I want to make sure that after each time that I do pop max, I no longer have two different trees of the same degree. So every time that I do pop max, I also do the cleanup and the merge. So I did a pop max here. Now I have a bunch of trees of degree 0. I have this and this. I merge them. I have this and this. I merge them. Now, okay, let me actually do it. I hate examples. Examples are hard to draw. Okay, so I had an 11 and a 6, and I merged them. Now let's say this was 20. So I have a 5 and a 20, and I merge them. And I just keep looking. So I'm too lazy. Let's say we don't have that. Okay, so now here I have a degree 1 and another degree 1, and actually I have another degree 1 here. It doesn't really matter. In some order, I want to merge them. So I merge these two that have degree 1. And 20 is larger than 11. So 11 becomes a child of 20. Now I have degree 2. I have degree 2 here. So I can merge these two that have the same degree. So 5 becomes a child of 20. I have degree 1 here and degree 1 here. I would merge them. So I had the 8 and the 2, and I merge them. I don't know, again, let's say I have some elements here. Now, again, I have a degree 2 and a degree 2. Let's say this is 9 to 5. So 9 is larger than 8. So I just make 9 to be the root. like that. And now I have two different trees, each of degree 3. So I can merge them. And the way I merge them is that 20 becomes the root. So just imagine that this is higher than that. I'm bad with examples. Okay. So why did I do this example? Because I wanted to show you that after we do this cleanup, we often end up with just one tree or a small number of trees. So since we're doing amortized analysis, if I do this Popmax, and after each Popmax, I do a cleanup. And by cleanup, I mean merging trees of the same degree so that we no longer have two different trees that have the same degree. And if I do this, I don't have to do it very often. And the number of trees really decreases in practice. But we have to prove some bound on this, otherwise it wouldn't work. Now, what is the worst thing that can happen when I'm doing a Popmax? So let's talk about Popmax again. I'm taking the maximum element, that's constant time. And then I'm removing the maximum element, which adds all of its children as new roots. Then I'm merging all the roots. Then I'm again taking the maximum among all the roots because I have to update the maximum pointer that I had. Okay. So when would this take a lot of time? It will take a lot of time if I have a situation like this. If I have my maximum element, and it's of course the root of some tree, but it has a ton of children, right? So if I have a tree like this is kind of my worst case scenario, because when I remove this maximum element, I'm suddenly adding a lot of new roots. And then because I'm adding a lot of new roots, I have to do a lot of new merges, and that's going to take more time. Okay, and these don't have to necessarily be like this. I mean, as long as you have a tree that is really wide and has really small heights, you have the same problem as here. Okay, so what should we do? We have to make sure that there is a relationship between the degree of the root and the height of this tree, or between the degree of the root and the number of elements in the tree. I want to make sure that the number of elements in each one of my trees is much larger than the degree of the root. Okay, because then I would avoid a case like this where I'm adding a lot of new roots. So how can I do that? Well, I can say that I don't allow any subtrees that have very few elements in them. But how can I enforce that? Well, the way I enforce it is using a rule that is called the marking rule. And the marking rule is very simple. It says if you are a node in one of these trees and you lose one of your children, for example, your child becomes a new root, then we will just mark you. We mark that you have lost one of your children. And we say that every node that is marked twice has to be promoted to root. So the idea is that if I have a node somewhere in one of my trees, and this node has some children, okay? And let's say for some reason, for example, I increased the key of this child and this child became larger than its parent. And this is not necessarily a root, it can have other things. So when I remove this child, I just mark this parent. Let's say I put a check mark next to it. I just remember that this parent has lost the child. And then if it happens again, if at some point in the future, this same node has a different child and loses that child, so if it gets a second marking, I would just grab this node, disconnect it from its parent, and make it a new root. Okay. Now, why is this useful? Because if this child, okay, let me give them some names. Let's say that this is U, let's say its parent is V, and let's say the children are W1, W2, W3, and so on. Okay. So if U loses one of its children, what is actually happening is that U is still contributing to the degree of its parent V, right? But now it's not really contributing as much as before in the subtree of V. So if at some point V becomes the maximum, I might have a situation like that, which I don't like. So I want to limit that as much as possible. But what I say is that I say, okay, if you lose just one of your children, that's fine. That's still enough children. I'm okay with it. But if you lost two of your children, now you do not have enough weight or enough number of nodes in your subtree to really justify the increase in the degree of V. So in that case, if U loses two of its children, I'm just going to disconnect it from V, and I'm going to say, U, you're now your own new tree. Okay. And this is also nice because, well, if U has lost two of its children, it has now fewer children. And I'm putting it as a root. So if at some point U becomes the maximum, again, I'm not going to have something that looks like that. So this is the intuition. So now I have fewer children for U, and I also have fewer children for V. Okay. So I apply this marking rule across all of these operations. So let's just see what happens with these operations. I apply the marking rule in push. Now, nothing changes there because push was just adding a new tree. Oh, and by the way, I would only mark non-roots. So if you're a root, I wouldn't really mark you anymore. Now, what happens with increase key? If I have a node and I increase its key, let's say the value was 5, and let's say its parent was 7. And let's say I increase this from 5 to 8. Okay. So I'm going to remove this, add it as its own root, as we said before, because we don't want to do bubble up. But after I remove this part and add it as its own root, I'm going to put a check mark on 7. I'm just going to remember that 7 has lost a child before. And then later on, if there is another one here, let's say this one was 4 and it was updated to 9, then 7 gets a second check mark. And so 7 is put as a root for itself. In a more general case, when I have some element here, and let's say that I'm increasing its value. So let's say that its value was X, now I'm increasing it to Y. And let's say that it becomes larger than its parent. Okay, I can look at its parent, that parent, and so on, all the way until I get to the root. So this is, let's say, my root. And some of these will have check marks from previous operations, and some of them will not. So when I'm increasing this one, because I'm not bubbling up, this one is becoming its own root, but then this parent has a check mark. So this parent gets its second check mark and becomes a root. So it's disconnected from this one. So this one also gets a second check mark, and this one is also becoming a root. So when I'm doing the increase key, actually my runtime is no longer constant, right? Because I'm starting here and I'm going up as long as I'm seeing ticks, and I'm making all of these into new roots. But I want to show that my amortized runtime would be constant. Now, in order to do that, I have to specify what my potential function is going to be, or how I'm doing my accounting. And so if you remember the potential method, what we would do is that we would assign a potential to the whole data structure, and then our amortized cost was our real cost plus the change in the potential. So we were storing some money again on the data structure, and we were using some of that money to pay for some of our operations, but not for all of them. So here's the potential that I want to define. So I want to say my total potential at any given time. I would say it's the number of roots plus twice the number of marked items. Okay, you will see why this particular potential works, because I'm going to analyze it. So what happens when I do a push now? Well, when I do a push, I'm just adding 1 to the roots. So my potential is changing by 1. And my real cost for doing that push was also 1. So my amortized cost, which is my real cost plus the change in potential, is also going to be constant. It's going to be 2, but I'm going to say it's constant. So push is still constant time. Max is, of course, again, constant time. We have a pointer to it. We don't really care about max. What about increase key? So when I'm doing this increase key here, I'm starting from here and going up, right? So this one is becoming its own root. But also all of the ones that had a check mark are becoming their own root, right? But the ones that had a check mark were contributing 2 units to my potential. And when they become a root, they're going to contribute only 1 unit to my potential. So whenever I'm changing one of these guys, one of the ones that had a check mark, to a root, I'm actually decreasing the potential by 1 unit. So in other words, this is paying for itself. I'm doing one operation and it's also decreasing the potential. So it's paying for itself. So I'm doing all of these operations for free. The only operations that I actually have to pay for is the first operation here, when I'm making this one a root. And for that, I have to pay just the cost of 1 because there is just 1 added to the roots. So my increase key is also going to take order 1 total cost in the worst case. In the amortized case, sorry. But now the problem that we have is what happens with our Popmax and how can we analyze that? How can we make sure that our Popmax works fast? Now, we did all of these things just to make sure that we can prove that our trees are large in comparison with the degree of the root. So here's what I'm going to do. Let's say that SD is the size of a tree that has a root of degree D. So I say, suppose that my root has degree D. I want to know how many elements do I have in this tree. Okay. So I have this root and it has a bunch of children, right? And the degree of this root is D. So for a second, let's just assume that we only had pushes. Let's see what happens if we only had pushes. Or no, actually, let's say we had pushes and Popmax. So let's not consider increase key for a second. If I have a vertex like this, and if it has degree D, what does that mean? So whenever I was doing cleanup, I was only merging graphs of the same degree, right? So this vertex, this is the vertex U. At some point, it got its first child. Let's call that V1. But what was the degree of V1? The degree of V1 was 0 because it's the first child of U. So when we were merging 2 degree 0 nodes. So V1 has no children. What about the second child that this node took? So when it got its second child, this was already a tree of degree 1. But we merge a tree of degree 1 only with other trees of degree 1. So this V2 was the root of the other tree of degree 1. So this V2 has 1 child. Now I can continue with this. I can say that if I have a V3 here, it has 2 children. If I have a V4 here, it has 3 children, and so on. Okay, nice. But this was all assuming that we don't have the increase key. But we also have increase key. So what is the effect of increase key? Well, increase key can promote some of the nodes, especially these nodes which were marked before, to become the new roots for themselves, right? So if I take, for example, this V4 here, it might be that it doesn't really have 3 children because some of its children might have been promoted to become their own roots. And let's say I continue this until I have VD here, okay? So, and the same thing happens with VD. it used to have d-1 children, but not all of them are there. Some of them have been promoted to root. But how many of them can be promoted to root? At most 2. Because if I promote more than 2 elements to root, then I would promote this one to root as well, and then this VD would not exist at all. So what can I say? Well, I can say that this VD has a degree of at least d-2, right? Because if its degree becomes d-3, it's removed and becomes its own root. The next one has a degree of d-1, and so on. And so this V4 is going to have a degree of at least 2. V3 is going to have a degree of at least 1. V2, well, this one becomes 0. V1 also becomes 0. Okay, so now for every node in my tree that has degree d, what I know about its children is that they have to have at least these degrees, this sequence of degrees. Okay, so now I can just write a recursion. I can say SD, the size of the subtree of any node that has degree d, is at least what? Well, this one has at least d-2 children. The next one has at least d-1 children, and so on. So this subtree has at least s of d-2 elements in it. The next subtree has at least s of d-3. And so on until we get to s of 2 and yeah, s of 1. And then we have these 2 last ones, which are only themselves, right? Okay, so let's take the worst case. Let's say that I have as few nodes as possible in there. Did I put no? So let's say that SD is exactly this much. If SD is exactly this much, then can I find the formula for SD? Well, here's the thing. This is the recursion for SD. Let's just plug in what s of d-1 is. S of d-1 is going to be s of d-3 plus all of these things plus s2, s1, 1, 1. So s of d-1 has all the terms in s of d except for this one. So s of d is s of d-2 plus s of d-1. Okay, and this is where the Fibonacci numbers come in. And actually, if you do the math more with a little bit more accuracy, you can prove that SD is actually the d plus second Fibonacci number. So it's not exactly the Fibonacci numbers themselves, but it's shifted by 2. Okay. So now I can talk about my Popmax. Now, if I have some tree of degree d, then I know that it has at least this many nodes. But what is this number? Well, if you look at f of d plus 2, it's easy to prove that this is more than the golden ratio of phi to the power of d. Okay, just look at the formula for Fibonacci numbers. So again, we're back to the situation where our trees are large. So the number of our trees is bounded. So when after I'm doing all those merges, when I want to find the maximum among all of the new roots that I have, I'm going to look in at most log of n different new roots. But the log is log base phi, where phi is the golden ratio. But anyway, we are doing O analysis, we're doing asymptotic analysis, so this doesn't matter for us. So now our Popmax is also going to take order log n amortized time. And you can do the amortized analysis with more detail. Like the Popmax takes an element, it promotes all of its children to become roots and then does the merges. You can just keep track of what happens to this function here, to this potential function. And you can see that actually the potentials get paid for all of the operations that we have, except for finding the maximum operation at the end. But at the end, when we're finding the maximum operation, we're going over at most log n different roots. So overall, this Popmax is going to take order log n.